So first of all, thank you so much for the warm introduction and also the great opportunity to present our work here. Yeah, my name is Shuzhe Wang, and I'm the fourth year PhD student at Department of Computer Science, Aalto University, supervised by Professor Yuho Kahara. So this work DUSt3R, geometric 3D vision made easy. This work, actually, this is the internship work at Naval Lab in 2023, together with Naval guys like Wensheng, Yanghang, Brace, and Joe. So the topic is mainly about the dense reconstruction. So let's start first with 3D dense reconstruction. So this is actually a key component in many computer vision and real-world applications, like in AR, VR, or navigation, also in some archaeology and also cultural heritage preservation. In the past decades, actually, we have the conventional solutions like this multi-view stereo to solve the problem. So actually, it gave a set of pulse and calibrated images of the thing. The target is to reconstruct a 3D dense representation of the thing. So we definitely have like very excellent tools like the CoreMap or OpenMVS, or also in the recent years with the development of deep learning. We think that we also have the neural-based one like the MVSNet, or also with the implicit representation like the nerve-based surface reconstruction. But all of these methods require the one common step is that they need to have the calibrated images, or at least they need to know the camera parameters. So, okay. So we have a problem is that what if the camera parameters like the intrinsic or extrinsic are unknown, or we need to do the multi-view stereo in the wild? Yeah, we have the solutions for that, which is the structural motion together with multi-view stereo. But for this kind of complex pipeline, you will have first key point detection, like description, or matching, or pulse distribution, or triangulation, or even bundle adjustment for the optimization, and to get the camera pulse, camera parameters, and also the sparse 3D point cloud. Then we do the multi-view stereo steps next to the per pixel depth estimation, normal estimation, and minimize the photometric error or the projection errors. So this is definitely a viable solution, but it's not elegant, right? Because this is a chance, a series like the minimum problems for each of the program. Actually, is not perfectly solved. It means that we will add noise to the next steps. And besides that, also we think that the two main components, like the structural motion and multi-view stereo, they may miss the communication between each other. So structural motion could definitely like the sparse reconstruction could help with the dense reconstruction, but inverse, we didn't find any like the information to use the structural motion to help with the sparse like the pulse distribution, or like the sparse points reconstruction. So this is one of the limitation, and also you know that this is a kind of complex pipeline. So it means that we require like a huge engineering effects to make it work well. Then we proposed our solution, which is the dense unconstrained stereo 3D reconstruction. So this is an end-to-end fully differentiable way to directly regress the point maps from a pair of image. So we make the pipeline much easier than just use a pair of image. The pipeline actually is a fully supervised training and fully supervised manner with large public datasets, include 8 open datasets with together about 8.5 million image pairs for the training. And it directly regress dense and accurate scene representation, so it's solely from a pair of image, and without relying on any prior information from the scene, like the pulse or calibrations. So we can see instead of use like the mesh the output, we output point maps that contains the the same geometry. So from the point map, we could extract the depth and also normals from of the image. And then we also know the mapping between the pixel and the 3D points because we have the dense prediction, which means that for per pixel, we have a corresponding 3D point. And also the relations between a pair of between the viewpoints. So since we have a pair of images input and we directly output the point cloud in a common coordinate, so we will definitely know the viewpoints between each other. Oops. Yeah, the network architecture actually is inspired by COCO, which is a cross-view completion pre-training pipeline that understands the spatial relations between the image pair. Here I'll give some simple like explanation here. COCO actually is a pre-trained network that conceived using a mask image and a reference image from a scene, but from different views. And what they do is the image reconstruction based on the reference image to do the reconstruction for the reference for the mask image. So in that case, actually the network will learn the spatial information between the two views and try to influence the transformation or between the two views. So this is how COCO pre-training, the idea of the COCO pre-training. So definitely our network is initialized by COCO pre-training. So similar to any kind of like a vision transformer encoder, vision transformer pipeline, we first have the we first classify the images and then to use here we use a common one shared autoencoder to extract the token representation from the encoder. So the encoder will share the weights, but for the decoders, we use two separate decoders to extract the information from image 1 and image 2, but they also share they have the information exchange. So during the cross attention stage, the information from image 1 will consider as an input for the cross attention layer in the image 2, and following by two heads like to predict the coord map and together with a confidence map. It is worth noting that here, instead of predict the point maps to two different coordinates, we predict the coordinate maps to a common coordinate, and then we can see that the first image, so the common coordinate, so it means that the common reference frame, we use the common reference frame of the image 1. So the second image actually is the point map of second image actually mapped to the first image. Oh, by the way, if you have any questions during the presentation, just feel free to ask it.
So excuse me,
yep.
Would you please go to the previous slide? So here you have a common coordinate, which means that it doesn't follow the camera view from either camera 1 or camera 2. There is a standard coordinate you are using.
Here we can see that the first image, we just use the camera pulse or camera extrinsics as the identity matrix. So which means we don't care about the camera pulse in the first image, but for the second image, they will consider a relative camera pulse between the two views for the prediction.
So you treat the first camera coordinate, and then is that the case?
Sorry, I didn't follow you.
So you consider that the image number 1, I1, has the standard coordinate.
Yes.
And then image 2 is relative, we have a coordinate that is relative to the camera 1, and then you use that to project the image number 2 to the coordinate of image number 1.
Yeah.
In the 3D world.
Yeah.
Okay.
Yeah. Okay.
Please.
I mean, I will please go ahead. So I think
in that case, please. So for point map, you mean that you have a point cloud representation of the images?
Yeah, for actually it's a very dense like the correspondence like for each pixel in the image we will have the corresponding 3D point here. So definitely, yeah.
So if in the point map you have the 3D location and the RGB value of that point and placed on the 3D space.
Yep, actually we don't predict the RGB because we already know the RGB from the original image. We just predict the XYZ.
Okay, so here you predict by point map, you mean that you predict the XYZ location of each pixel.
Yeah.
Okay. So here you have information exchange. That means you will utilize the stereo information to estimate the locations of each pixels in I1 and I2.
Yeah.
Okay, thank you.
Yeah. So our network action is asymmetric, which means that we know since the decoders, like the decoders for first image and second image, they do not share the weights. So the second decoder definitely know it need to predict the mapping from the second view to the first view.
Yeah, some further questions. So
Oops.
did you suppose you know the relative camera pose between the two images?
We didn't consider about the camera pose during the training procedure. Instead, we directly use the ground truth point map, which will definitely include the camera information, like the pose, relative pose. Yeah.
Yeah. So another question is that for a pair of images, do they have the same relative camera pose, or their relative camera pose differences are different in different pairs?
Well, I didn't follow the question, but I think for a
Yeah.
pair of image.
Yeah. So I can try to clarify. So,
Yes.
for example, you have 100 pairs of images. For those 100 pairs of images, do they have the same relative camera pose? For example,
You
5
mean
degree.
no, we didn't do that. Actually, what we did is we use the like a matching algorithm and also the image retrieval to generate the image pairs. So we do not fix the camera pose, like fix the degree or like the translation of the relative pose, the pair of image. Yeah.
Okay, so you will have different relative camera poses.
Yeah. In that case, action is to increase the diversity of the like the images, the image pair.
Okay, so even if you have different camera poses, you still assume that the information exchange can help you to identify the relative camera poses and and provide you with the correct point map, especially for the image in camera 2.
Yeah. This is also has shown in Coco pre-training, like the neighbors previous work in Europe. Yeah.
Okay, thank you.
Oh, hi. Can you hear me?
Yep. Yeah.
I have a question. You mentioned that you will map the point map of the camera 2 to camera 1, right? But I am wondering whether the point map coordinates of the camera 1's coordinate system. Will the coordinates be normalized, or are they just their real size, real size scale?
Okay. This is the training objective. I will mention the later. So definitely we will rescale the coordinates, like the common coordinates and also the ground truth coordinate, because we want to avoid the scale ambiguity. Yeah.
Okay. Thank you.
Yeah. So let's move ahead. Then here we mentioned the data set and training objectives. As I mentioned in the previous slide, that we have 8 large scale data sets that include indoor, outdoor, object centric, and synthetic and real data. So together we have 8.5 million of the training data. So here, this is actually the answer that about the image pairs. So we utilize like the image retrieval and also the matching point matching algorithm to match and verify the image pairs to keep like the image pairs. They could have like the reasonable overlap. And the ground truth map are obtained from the ground truth camera intrinsics, camera poses, and also the depth maps. And then here is the training objectives, like the regression. Definitely we directly regress the 3D point map. So it's the optimizing the Euclidean distance. Here X is the ground truth point map, and X bar actually here is the predicted point map. And we scaled it with the average of average distance of the points to the origin. To avoid the scale ambiguity between the prediction and the ground truth. So this is also the answer to the previous question. And also in order to handle the EL-defined 3D points like the sky, we also extend the regression loss to a confidence-aware loss, which is proposed in 2018 and has shown to be efficient to add the to predict the confidence map without any like the additional supervision. And here we force the confidence map to be positive, so that the network could have to explore the harder area, because if we have no confidence to the prediction of like the hard areas, for example, like the areas with only one view coverage, so they do not have any like a common views. The views that do not have any the cameras that cover the area. So if in that case, actually, they will penalize the prediction with no confidence. And besides that, we also propose the global alignment because in the previous slides, so what we are handling is just the monocular and also the bilocular stereo reconstruction. That if we have multiple views, here is we propose a fast and simple post-precision optimization for the view multi-views. Like it could be super fast and can converge in only 300 steps. And so for multiple views, we first built a complete graph for all of the pairs, and then it jointly optimized the 3D point map together with the pairwise pose and the scaling. So here we have the chi, which is the 3D points in a common coordinate that we wish to output, and we have the scaling vector, and we have the pairwise the camera pose, and also this X is the prediction from DUSt3R. So it's weighted by the confidence map. So the objective here is trying to minimize the distance is still the 3D distance, is still the Euclidean distance in the 3D space to get the chi, which is the 3D points in the common space. So and then if we wish to extract the like the camera parameters, for example, the intrinsics and also camera pose, together with the depth map, we can replace the chi here with the like the projection function from intrinsics, extrinsic, and also a depth map. So together we optimize 5 parameters to get the fellow like the 3D point map in the common space. Also, we evaluate our methods in a bunch of like downstream tasks. The first one is about the point matching. So since we predict the 3D point actually to a common coordinate, so the 2 points like from different views but very close to each other will be considered as the image pair. So we just use a mutual nearness neighbor search to find the closest 3D points of the 2 views, and then we consider them as matches between two views. And the other application is about recovering the camera intrinsic. So since in the first view we consider it as the next standard reference frame, which means that we have the extrinsic as the identity matrix. So in that case, we don't care about the camera intrinsics or camera extrinsics, and we just use the reprojection error here to minimize the reprojection error and to get the focal length, to estimate the focal length of each pixel. But we will get our fellow prediction as the average, like the average of the focal lengths. So we evaluate our the predicted focal length on 1,000 random images from edit from blended MVS and Code3D with the average absolute error of the I4V, and also the 2D reprojection accuracy. So here we find that we didn't compare with other methods here because this is the experiments required during the rebuttal. So we just provide our methods on the both molecular and bilocular estimation. And also we have the downstream applications in visual localization. So the task here that what we did is about to give a query image, and also what we did is to first retrieve the database image. And the task is done by first, since we already built the pixel correspondences from the point matching, and we also have the camera intrinsic estimation from the previous method. So we could obtain the 2D to 3D correspondences of the query image and the 3D database. So the camera pulse then is solved by the PMP runtime with the estimated camera intrinsic. And also another approach is to estimate the relative pulse by the point match. Since we already have the correspondences between two images and also the intrinsics, we could directly estimate the relative pulse between the two views. And then we could convert the pulse to the word coordinate by scaling. So the scaling means that actually for the predicted point map and also the ground truth point map of the database image, we could scale them by the median views, and then to convert it to a word coordinate. So there are two approaches to do the visual localization task, and we selected the first one to present the results here. Actually, we achieve comparable results compared to like the direct end-to-end methods. And some of the methods like the DUSt3R style, chasing net, they are trained on the specific thing and also evaluate another thing. But our model had never seen any information from the services dataset and the Cambridge dataset. Then we have the multi-view pulse estimation. The task actually is which is proposed, I think is not from, yeah. The method which is very popular last year is from the pulse diffusion. So we also have like the two ways to extract the multi-view pulse camera pulses. The first is to directly obtain the relative pulse by the relative pulse estimation, as I mentioned. And also we could extract the pairwise camera pulse from the global alignment to get fellow pulses, relative pulses of multiple views. And our methods here like achieve the SOTA performance on Code3D and the realistic 10K dataset well. Like the traditional algorithm like with COMAC with superpoint and superglue, or like the pixel strap motion, pixel perfect strap motion, they may fail in this case or achieve low accuracy, but we could still have very high standard for the pulse for the relative pulse distribution on like the relative translation accuracy at 15 degree or translation rotation accuracy at 15 degrees. Yeah, then we also have the monodepth distribution and the multi-view depth. So for the monodepth, since it's also easy to be achieved because since our first frame is a standard frame, we can simply concede the Z value of the predicted point map at the depth map. And then for the multiple view depth, actually with we rescale we again rescale the depth prediction. So okay, I think that I may give a detailed explanation here about the traditional the other algorithm. They either require the ground truth camera pulse or ground truth range to do the alignment. But in our case, our alignment just use the scaling factor of the median views of our depth prediction from point map and also the median views of the ground truth point map, ground truth depth. So to do the alignments, and then we also achieve the SOTA performance here. Yeah, here we also have the 3D reconstruction, the two views, and also the dense reconstruction. And we could even achieve some the reasonable results if we have the offset view, which means that it's nearly 180 degrees. And what's the most surprising thing is that even without overlap, here is an example of that. We took two pictures from an office, but without any overlap of the two images, we could still get a reasonable reconstruction of the room. Our results, our 3D reconstruction results here does not achieve as good like the traditional or the learning-based methods on the accuracy and also on the completeness. Here the accuracy is in millimeters, and also the completeness is the same in millimeters. But the other methods are what we tried. They all requires the ground truth cameras for the fellow prediction. But in our case, we don't need any kind of we just use the predicted information from DUSt3R to do the reconstruction. Yep. So here are some more visualization videos about our method. Yeah, our method actually directly output the point map, so dense point map. So we don't further fine tune any kind of from point cloud to mesh to generate a mesh the method using the matching cube or the Poisson. So the next step if you wish to extract a high quantity mesh, you may need to use some kind of most recent learning based or SDF based method to do that. So in conclusion, actually we presented first end-to-end 3D reconstruction pipeline from uncalibrated and unpulsed image pairs. And we introduced the point map representation for MVS application. So it enables the network to predict the 3D points while preserving the implexual representation between the pixel and the scene. So which means that the pixel and the point cloud cross-boundaries. So we also introduced the optimization procedure for the global alignment in the context of multi-view 3D reconstruction. So the pipeline, so in this procedure, actually, we could extract the intermediary outputs, for example, the depth and the camera pulse or camera intrinsics of all the classical structural motion of an MVS pipeline could do. So and we also evaluate our pipeline in a bunch of in a range of 3D vision tasks. So and our method actually achieves SOTA results on both molecular and multi-view depth benchmarks, as well as in multi-view camera pulse distribution. So I think like we have some further directions about this work. So the first is about the improved prediction accuracy. As we have observed that our prediction in outdoor actually not that accurate compared to the core map reconstruction. We think that there is a data training imbalance between the indoor and outdoor. For outdoor things, although we have like the blended MBS, we have neck depth, and we have the Waymo data set, but we still find that the depth information in those things or in those data set actually most of like the depth information are missing. So during the training procedure, so we consider this is the imbalance of the training. And besides that, this will directly use a regression to get the point maps, but the regression loss actually is proven to be not that accurate compared to other methods. So, and also we could focus on and kind of like the global to local predictions that you try to predict the details of the 3D maps in more accurate way. So that may be the future directions for the improve the accuracy of the point maps. And also another problem is about the memory efficiency. In current stage, we can just handle or for a single like GPU with 12 gigabytes memory. We could handle like less than 20 images because of the global alignment. And so in that case, what we need to do in the next step is to build a memory more efficient way, either by like using knowledge distillation to train a small scale network, or other engineering effects to make it flexible to handle larger scale to more views on the larger scale for the larger scale reconstruction. And then we also could combine it with the 3D foundation as the 3D foundation models, like adding more training data and downstream tasks by adding like the human data set, like the human pulse, or also to add kind of information from the to make them more balanced for the outdoor thing training. And also for downstream tasks, I think that since we got the point cloud, this point cloud from DUSt3R, we could directly use it for Gaussian spreading, and also we could use it for like the 3D thing understanding or different kind of tasks in 3D. Yeah. So yeah, thank you for your attention, and our code and mode are available at GitHub. So if you are interested, you can take a look. I think also if you have any questions, I'm very glad to answer.
Thanks. Thanks for your great talk. Any questions?
So I can stop the recording, then we can do the QA section using Chinese, since it's more direct.